Hey, good morning, everyone, and welcome to today's kind of new series that we're doing here at Technical Toolboxes called our Quick Technical Talks. So these are meant to be just quick, digestible series, a series of information where you're going to get, one topic that we want to be focused on at, a intermediate, maybe beginner level, and have as much dialogue as possible with our experts here. So today, we've got Joe Pikas on the line, the man that needs no introduction from Technical Toolboxes. Our first talk here is going to be on AC mitigation. So just kind of some housekeeping items as we get in. This is maybe a new interface that you're seeing here from us Technical Toolboxes. If you want to submit a question, we want to make this session, more interactive than our old webinars. So if you have questions throughout, just add them on the Q&A box on the upper right hand side. Joe, I will, if there's a good question that we want to talk about in real time, I will just call it out for you. But
Thank you.
we want you all on the phone to just kind of get out, as much out of this as possible, and that starts with high interaction. So with that, I'll pass it over to Joe. And yeah, look forward to the questions throughout the presentation. So,
Well, thank you, Nick. I appreciate it, and welcome everybody. And one of the things, like Nick said, let me see with this new way to bring it around. I'm not able to move my screen around. That's interesting. Let me try something here. Nick, I can't advance my screen here. Is there a secret here?
um, Joe, you might be in the wrong window if you want to move forward that way.
Um, yeah, I'm not sure either window. It's not advancing.
Okay,
Oh, there
why
it
don't
goes. There it goes. Okay.
you? Right.
Sorry, everybody. I don't know what I did, but obviously it moved. So thank you. Uh, we're going to talk about the agendas are going to include a definition of mitigation, and we're going to talk about the types of mitigation too, or grounding. And I want to discuss the types would include a discrete anode, and that's something that it's used quite a lot. Where we're trying to bring down spikes in the voltages and things of this nature. So 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 we're going to be talking about single anode as well as deep anodes, and even casings, and how to utilize them. We're going to talk about distributed vertical and horizontal anode strings. This is a powerful one. And with the new technologies of using ground rods and bringing the cost down versus regular conventional CP anodes, is really taking hold in the industry. The other one we're going to talk about, and the same thing, is the linear placement wire or cable. And copper wires is really taking over versus zinc, because zinc started off in the industry because we didn't have decouplers. Well, now that we got decouplers, well, copper wires are a good a good alternative. And probably the biggest one that we get a lot of questions on is pipeline bonds. When do we use them? How do we connect them? Where are they? What areas did need to be done, and why do they need to be done? And we'll discuss that. We'll talk about decoupling devices, AC mitigation, and I'll talk about some of the old cells that we used to use, with potassium chloride, and why they went to disfavor. Mitigation to meet the AMP or industry standards, gradient control mats, and then I have some examples to show. And specifically with all of the things that I just discussed above. including steady state induced foliages and fault foliages and currents. And then we're going to end up with a Q&A session. Okay, I did something to advance it, and I don't know what happened, and I'm still having problems, and I don't know why. Is there? There we go. I guess
I'm still seeing the agenda slide, Joe.
I not able to advance for some reason. Uh, Not sure why. No matter what key I hit, I this is my first time on this new program. So
No
and
worries. Hey Joe, how about I'll go ahead and share.
okay,
And sorry about this, folks. And
yeah,
we'll go that route.
yeah.
So,
Some reason my computer is not advancing.
okay.
There we go.
There we go.
Okay, next slide,
Slide,
please.
please.
Oh, we got feedback.
All right. 1 second, folks.
Well, this is anyway one of the things that we'll be talking about. Why Nick is trying to advance my slides is discrete anodes, and we're using them. I'm going by memory. Uh, it'll come up uh, on the next slide. Uh,
Joe,
what?
I need 1 minute. I need 1 minute to rejoin, and folks, we'll be live again here with slides in 1 minute.
Oh,
So
okay,
go ahead and talk from memory, and I'll be right back.
okay. I'm. Let's see if. Yeah, that and we never ran into this kind of issue here. So uh, anyway, regarding discrete anodes, um, we use them uh, usually at peak voltages. You know when we're trying to bring them down at the beginning and the end of the pipeline. You'll typically find peaks. And what's the one of the best ways to use them is if you have an isolating device at a station, like where the line starts, as an example, you could put a decoupler across that isolating flange, and that could act as a discrete anode. Another thing we could use is casings, okay, case crossings.
Hey Joe, I'm
You,
back with the presentation. So,
oh, there it is. Okay.
okay, yeah.
Let me bring that over towards me over here so I could read it. Okay. Um, yeah, the other thing we could do is use uh, the discrete anodes to put on casings, and if they're at a high peak voltage area, that'll work. The big thing with with casings is that if it's already shorted, you could have a problem DC wise as far as your cathodic protection goes. So keep that in mind, regarding case crossings. However, they will dissipate the AC. And what kind of effect do they have? Generally, approximately 500 feet, but it's okay. I'm jumping. What's going on here? Here we go. Um, yeah, I lost my. Oh, here we go. There. Uh, also, we have to keep in mind that with case crossings, uh, we have to keep in mind that where they're located. So keep that in mind, as far as personnel safety and how you set up your decouplers and things of this nature. Like I say, they will bring down an area of at least 500 feet or more, and they're used in electrically isolated situations. The other ones that are really coming into favor, and why, is because the cost is distributed vertical or horizontal anodes, particularly the vertical ones where you could use a single ground rod, and they use conductive concrete or bentonite clay, to surround them to bring the resistance down. So example, if we have a resistance to earth of one single anode, you could put that in there, and let's just say we use 50-foot spacings, and uh, over the length of the section that we're trying to protect. Um, and where do we get this from? Well, usually uh, it's usually the spacing is set upon the physical length of the anode itself, to minimize the mutual coupling. So as long as you have greater than that length, 4 times that greater length, you you could have a more effective system by using these anodes. And the nice thing about it is we kind of recommend, depending on the current drain that is occurring, is try to use decouplers at least at a 2,000-foot level. I mean interval, and this is important to making it more effective. The thing about the AC power toolbox mitigation is that you could you could create multiple scenarios in minutes to see which is most effective, whether it's ground rods, using a linear placement wire, or whatever method, and 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 just go back and forth and determine the optimum spacing, the optimum resistance, and the optimum cost of installing these. So this is nice where you could make these changes in minutes rather than hours playing around. You have that capability to do that. Nick, could I go to the next slide, please?
Yeah, and before we do that, Joe, thank you, Mohammed, for the first comment. Joe, if this is a quick answer, maybe we do this now just while we're on the slide, but otherwise we can do it at the end. The question is, how to select the appropriate decoupler rating and specifications when AC mitigation is needed? What are the
That
parameters? Or, yep.
uh, Go ahead. Yeah.
What are the
Okay.
parameters of survey evaluation that help to identify these specifications?
Yeah, we're gonna talk about decouplers in a couple minutes, but
Okay.
just FYI, decouplers uh, are usually rated about, whether it's a decoupler or a PCR, polarization placement cell. Uh, they're rated about 45 amps to drain, and the PCRs, the polarization cell replacement, are can go up to 80 amps. So you need to talk to Dairyland, the biggest distributor in the world. They do Siemens grounding for substations and GE too. So these guys actually use them too. So they're probably one of the best companies in the world to use. So it check with them. They have some great engineers that could guide you, based on the current. One of the things I wanted to point out is when and you'll see it in my examples, is we have a thing called, not only do we have induced voltages for steady state, but we have induced currents. And if you look at the induced current on your outputs or your results or your graph, uh, that will tell you how to size your decouplers. In other words, the current is going to increase once you install mitigation. So that's the value that you want to use when you set up your decouplers. So I just want to point that out. So check that out, and you'll be able to determine how many decouplers you could put in there, and you could split it up accordingly. So I didn't want to get too much into it, but since you mentioned it, I wanted to bring that out. As I stated, zinc ribbon was originally used 30 some years ago, or even earlier, for AC mitigation. However, it didn't have decouplers because we didn't have them that far back. The ones that came out, way back then, were the potassium chloride, and they had plates in them. And the biggest problem with them is if you didn't maintain the potassium chloride levels. Okay, I lost something. I lost the presentation. Um, if you didn't have the potassium chloride levels, um, what would happen is they would dry out, and then you would have problems. They'd burn up. Another issue was they were constantly leaking too. So that was another issue with with these devices. So that's something you had to deal with. Also, how do we calculate these things? If you're using a copper cable, let's just say a 2 watt, and you know you're going to have to drain some couple hundred amps, uh, you could really get some very low resistances, like a linear anode of in a 5,000 ohm centimeter soil. And technical toolboxes has those programs in our pipeline toolbox called cathodic protection, and you could use those calculations right from there. You could look up a horizontal anode for whatever number of feet, based on the size of it, whether you're going to use backfill around it or not. Uh, you know, everybody knows about the mitigator, so I'll just mention the name. And it's usually used in higher resistant soils. So keep that in mind. You could and these calculations are done by the Sunday or the DeWhite's calculations, and they're in the toolbox. Also, if you're just using zinc, and if you want to use zinc, that's not a problem. You could just check the box, and if it's a typical zinc ribbon, you don't necessarily have to put the resistance in there unless you wanted to. Say it's a thicker or heavier type of zinc, then you could add your resistance values in there. So I just want to let you know that we have these capabilities, to go on this. Like I said, it's been used in the past, but the problem is that because if it is part of the CP system where you're using galvanic anodes, you could have premature failure of the zinc, and sometimes you can get passivization if it's not used. So there's a lot of things that you have to think about before you use these type of products. Another thing. Oh, by the way, I've uh, in my former life I've done some designs. Uh, 20 years ago, and I've used copper wire, and guess what? It's still operating with no issues. So I could tell you that for a fact. So I know some people they're scared of the cost, but when it comes to replacing zinc, there's a bigger cost in that. Uh, One of the nice things about the program is you could use the combinations of a discrete, distributed, and parallel type grounding. Okay, I want to use the word grounding and not anodes. Okay, because really that this is what we're dealing with. But an anode is a ground too. So either way you want to look at it. Um, but um, but for the purposes today, we're going to just call it grounding. Okay, and of course we need to think about when we're designing the geometry of the pipes, and transmission lines, the workspace, resistivity, and other constraints in that area. Okay. Nick, can we go to the next one, please? Okay. This is my favorite one because it's ignored. And of all the ways to reduce the voltages on the pipeline and mitigate, it's called pipeline bond connections. And one of the things we're recommending is test it out first wherever your connections are. And your connections could be bonding is recommended at the start of each section, or where pipelines are bonded together at valve stations or at crossovers, customer piping, CP rectifiers, and of course other stations and where you have decouplers. So if you have a multiple pipeline right away that you're going to bond in all the pipes to mitigate, this is what you should be doing. Is thinking about making sure these bond connections are in. Now we get a question to say, well, Joe, we put the bonds in, uh, but but we have a problem. There was no change. What happened? Well, it could be number one. It could be that the pipes are the same diameter and same coatings. Particularly, one of the things we found uh, uh, was with the three-layer system, the three-layer coating systems from Europe. Uh, they tend to not have an effect compared to some of the FBEs and things of this nature. Also, the diameter size when it was put in, and other types of coatings. So when you get mixes, and also proximity. So will bonding um, help in some cases? Yes. And will it remain the same as if it wasn't bonded? Yes. So depending on how your pipeline is set up, uh, everybody has to text me when I'm, I'm giving a class here. So keep that in mind. If there's no effect, don't be surprised, and if there is an effect, don't be surprised either. Okay. So I bring that out. Okay. The other thing is try to when you're doing pipeline bonds, they must be modeled first before mitigating the pipelines, and then you could turn them on and off and things of this nature. If you could bring up the next slide, Nick. Thank you. Okay. And what I'm showing is these decoupling devices. There's a lot more than this. I'm just showing like the two major ones. Okay. And like I say, they're good for about 45 amps of AC. So think about that. You'll have to get the specs on the what they are for the faults. And remember, a fault is could be most of the time it could be in microseconds. But if it's a fault from the power lines touching each other, then it's going to be in milliseconds. So we got two different faults, one from lightning and one from how could I say poor maintenance or design of the power lines. So we got those issues to think about. Most of the stuff is lightning uh, and remember, it's sizing of your cables also needs to be done based on where you're located and but it's instantaneous. So this is why we're using these decouplers. Now the decouplers use both for steady state to drain the induced AC voltages and currents, and it's also used for faults. And we're going to discuss that in a few minutes. The next slide. Okay, one of the other things we talk about is gradient control mats. Okay, and we're concerned about the touch and step potentials. Okay, this is the big thing that we're dealing with. However, the most programs are not designed for for this type of arrangement because this is very specific to locations like this, like a valve station. So keep that in mind that we're dealing with a different animal called IEEE 80, and what we're trying to do is put in these gradient control mats. As you could see that they are they're a grid type of setup with the decoupler over on the side here. Okay, that little black device, and then it'll be backfilled with crushed rock and things of this nature. What you're trying to do is make a high resistance situation so the personnel don't get shocked. This should be considered first before you do anything. If you have voltages that are over the 15-volt AC range, this is a different type of an animal. You need to be thinking about these at test stations and areas like that, above ground valve stems we mentioned at risers and other pipeline components that are or appurtenances that are above ground. Okay, so I bring this out because uh, uh, this is going to be critical also to your design for mitigating the corrosion and the faults on the system. So you're trying to reduce some things, uh, and remember when lightning hits the towers, um, most of it goes to ground, right? A good deal of it goes down to the shield wires and spreads out that way and tries to go back to the substations and things of that nature, or additional grounds along the tower line. So how it goes, depending on the resistance, the maintenance of the shield wires, the maintenance of the grounds, all play a big role, you know. So when we calculate, and we're going to get into that in a minute. The next slide, Nick. Uh, yeah. What? Uh, Let me pick up on this. I'm going to show you what we have here, and we're going to expand on this. But what we recommend is when you put your section lines, that's these green lines right here. I'll zoom in. All these little green lines at the where the towers are located. So when we do a fault survey, one of the things not only we create sections for you know, uh, based on soil resistivity and things of this nature. But we also base it on where the towers are located, where the geometric changes are, on here. So what we're going to be talking about is this pipe one and pipe two. Pipe two comes in the right of way and leaves. But more importantly, we create our section lines, and like I said, even resistivity changes. If there's lakes and ponds and streams and water bodies, we need to think about those type of things. So what we have is this blue line. That's the power line. This is pipe one. This is pipe two over here, and this is where we're starting. This is where we're starting our survey. We just happen to have a compressor station located there with isolating flanges. And also this line continues on, and so does this one. This comes in and goes out. And I use this as an example. And why did I use it as an example? Well, in the next slide, I'll show you because we're going to we're going to model it, and you're going to see um, what's going on here. And this is the what we call the unmitigated steady state volts, amps, and current density. And where's the current density? Well, the volts for pipe one is the blue one, and I'm going to focus on the current density over here. And then the green line is the current density, and you can see it's well over 30 amps over here on both pipes. Both pipe. This is pipe one, and this is pipe two. This is the pipe that comes in the right of way and leaves the right of way. Okay. The red line, this line here is your current is your induced current, and the other one up above is your um, induced current for line two. Okay. So this is what we're dealing with. So how do we mitigate this thing? One of the things that we do is we've got to reduce those areas of concern. And remember, I said a discrete anode um, at the beginning of the system would take care of things. Look at the voltages here. It's over 20 volts, over 30 amps per meter squared for both of them. Okay. So on the next slide, we're gonna see on the mitigated side where we're gonna have three different types of mitigation and bonding at all of those points that we talked about. Okay, we had bonding where that pipeline came in, but the red one. Let's see if I get in here. Oh, here we go. The red one right here is 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 this one right here. That's a discrete. And look what it did to that 20 volts, knocked it down to around 3 volts just by putting a decoupler across that isolating flange. Amazing, isn't it? And this is the nice thing. It just takes one click, and I want to put a decoupler there. Just take unclick, uncheck the box, and it's gone. If I want to do uh, mitigation for over maybe 3 or 4 nodes or sections, all I have to do is just hold it down and click once, and I could do 3, 4 sections or whatever I need to do. Or maybe if I need to do the whole pipeline that way, we have the capability. What I'm saying is the flexibility is there to do different scenarios to come up with the most cost-effective way to mitigate as well as well as to bring the costs down too. I elected to use uh, the distributed anodes. That's this guy right here, and here they are right here. So look what it did here, how everything it dropped everything. And this is why I'm saying distributed anodes are pretty effective compared to even sometimes the linear placement wire. I'm going to call it that because basically it's a contiguous cable just running down or zinc running down the right of way. These are distributed. Let's just say ground rods, whatever distance that you spacing that you put in for the full length of the section. And it's amazing. And if you notice what happened with the current, it went up. And why did it go up for that pipe two? Is because we're draining more current, but yet we're reducing the voltages on the pipe for both pipe one. That's this guy right here, and here's your pipe two, the short one. Okay, where it comes in and leaves. Now I deliberately put in the um, the parallel mitigation over here. And you notice it doesn't quite have the effect of the other ones. It didn't bring it down as much. And I just wanted to show you the difference. So if I wanted to just switch this out with this, take a half a, you know, 20 seconds, 30 seconds to do it. That's how quick it would be. And then I could just run another scenario. I could just uncheck the box and check a new one. How long would that take? And I could run another scenario. Oh, and then knowing the cost of of what's going on here, you could see this type of thing. One of the things I'm going to be doing at NACE or AMP next year in Nashville, Tennessee, is I have a paper called reconducting. Okay, and reconducting is something that's occurring in our industry with the power lines. Not only in the uh, uh, not only in the co-located right of ways, but what the power companies are doing is replacing their cabling or conductors, and they're gonna be able to go improve their power capabilities 3 to 4 times what they were before with the same towers with just minor changes. Their payback on that is going to be within 6 months. So could you imagine taking a 1500 amp system and running it up to 4500 amps or 5000 amps, whatever, with the same conductors? And what do you think that's going to do to your pipeline? That's what I'm going to talk about next year in Nashville. Reconducting remote and co-located locations. So watch out for that. I'm putting that paper together as I speak. So I just wanted to point that out, but just to show you how quickly you could mitigate things. Let's see, what do we have here? We got a fault, and this is the fault, and I selected the closest tower to the pipeline. And if you noticed in this area here, we're running about 15, a little over 1500 volts. Same thing here, about 1600 volts. And if you look and see, um, uh, that's not a bad thing, but this is unmitigated. And what did we do just before? We mitigated the system. So Nick, if you could go to the next slide, and we're going to show you the mitigated version of it. And it's the same points that we had before. And look what the mitigation did in this to bring down the fault current and voltages. And this is the voltage across the coating. And when you bring the voltage across the coating way down, you also bring down the step and touch potentials too. They follow along with the potential rise or surface potentials, whatever term you want to use. And you could quickly see the impact of what's going on here. So without further ado, Nick, I think the next slide is yours. If there isn't any questions, did we get any questions come in?
We do have some questions. I think before we kind of go to our standard question format, just kind of the quick word from our sponsors, so to speak. So, what we do at TT, we do a lot of software. We do a lot on training, as you've seen here today with Joe. We do just want to highlight we do have a Training Hub Premium Pass, which for us is an all-inclusive premium pass with well over 150 hours of content for professional development hours, customized learning pathways, as you can see on the screen, depending on what stage your career you're at, as well as learnings around stuff like AC mitigation and recommended pass there. So a lot to see there. We did just want to ask, if you would like a free trial, 2-week trial of that premium pass to see everything there is to offer. There's a lot of live classes with Joe in there, a lot of on-demand classes as well. We're just going to put up a quick poll. Just if you reply yes to that, we will send you a link to give that a quick look. And if no, don't worry, we will leave you alone. So no worries. So as we'll give people 30 seconds to vote on that, just with what they want to do. For everyone else, why don't we go to questions? So Joe, let me look at the first one here. This is going back to AC decoupling as an AC mitigation method. So when to use an AC decoupler as an AC mitigation method. I'm asking as some claim that installing an earthing zinc anode will be enough to solve this issue. Is the latter correct? How to choose the right AC mitigation method when AC interference is in place?
Okay, yeah, that was one of the points that I brought out about uh, zinc. Is that number one is that you get premature failure when you tie it to your CP, as part of your CP system. So if you're using galvanic anodes already, okay, uh, uh, the history has shown that zinc will uh, fail prematurely, because it becomes part of the anode. And what is zinc ribbon? It has a steel core in it, right? And it's not the best conductor in the world as compared to copper. Like I said, the power industry 75 years ago uh, chose to change out their zinc grounding to copper, and that hasn't changed. They didn't never change back. And then also zinc has a tendency to passivate. So 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 if it's not used as an anode, and that's what it's supposed to be, because it has electrochemical potential to steel, of 1.1. So keep that in mind, with zinc. I would always use the decoupler, whether it's zinc, copper, whatever material you're using, just to keep it separate and not have a premature failure or anything like that. Next questions, Nick.
Yep. Let me. What standards shall be used when dealing with AC interference survey, implementation, assessment, mitigation, and more?
I missed the first word, a couple
What,
words.
what, what standards should be
Oh,
used?
oh, that's a great question. Um, uh, let me be Uh, yeah, there's many standards, and of course, probably the most basic one would be uh, meeting the anytime that you have from a regulatory perspective. Let's take it from a regulatory perspective to an industry perspective. The regulatory perspective is if you find uh, an interference problem, okay, or where you could have metal loss, okay. From a regulatory standard, you must do something, okay. So that you have to take that as number one. Uh, uh, Provided and most pipelines are now coming under under the rulemaking. From an industry standard, you would base it on the type of potentials. Or in the case of current density, um, we have current density criterion that are out there. They're different levels. Of course, it's based on also how much DC current density you have on your pipe, too. So it's a combination of two different standards. If you have more than 1 amp per meter squared DC, uh, you start polarizing your pipe, and it becomes more alkal. You create an alkaline environment. So you really need to use that 30 amp per meter squared or lower, even lower, depending on how much is polarized and the chemical change that occurred, depending on the amount of uh, polarization and changing that environment around the pipe. So uh, so keep that in mind. The problem is this is why you need to have coupons. This is why you need to have things where you can monitor these what's going on the pipe. So, but once that's recognized, and then also you have another standard for safety. So you have an OSHA standard for 15 volts. So there's many ways to look at that question. Okay.
Awesome. Thank you, Joe. Okay, we promised a short and sweet presentation today, and we are at time. So thank you all. If you do have additional questions, kind of about what we covered today, feel free to reach out to us, and we will get you in contact with Joe. You will get a copy of this presentation later. And with that, we hope you all have a great day, and we'll see you at the next quick technical talk. Thank you very much.
And thank you, everyone. Sorry about the little bit of a hiccup with the I couldn't change the slides around. That never happened to me. So thanks. We appreciate your patience on that one.